Thank you, Matteo. Thank you, Alex, for herding us together, as usual. So I was just talking to someone, and the complaint was, well, we kind of need to see how to do things, not exactly, what is the background. Unfortunately, this talk is going to be about a whole lot of background, a lot of details. But hopefully, I'll try and provide some intuition. Yeah? So I don't do a lot of theoretical work. But this has actually been one of the exceptions. The problem is quite simple. I'm just thinking, mostly talk about model selection for high-dimensional settings. And by high dimensions, I usually mean when the number of predictors actually goes up with the number of observations, right? So in general terms, oopsies, I'm doing something that I'm not supposed to do. There we go. So I was overly optimistic on the use of this. Anyways, so the kind of questions I'm going to try and, I don't think answer, but at least address are quite general. And of course, as you'll see, we'll get boring and specific very quickly. The idea is, well, we're thinking about situations where gathering data is becoming easier, at least in some cases. And so the question is, of course, it's a bit of a classical question. So as data grows, what are the upper characteristics of statistical procedures? And by statistical procedures, I mean model selection procedures, in the sense that they tend to be assessed a bit less precisely than standard problems. Particularly, we worry about the case where the number of predictors, so for example, you can imagine the number of genetic markers associated with a particular condition goes up with the sample size. We'll see whether that's meaningful or not actually in applications. Short answer, probably no. It's unlikely that your number of genes is going to go up with the number of subjects. But it's got some finite sampling consequences that perhaps we ought to think about. And then, of course, the idea is that there's often a bit of a separation between model selection and then final estimation. You're all familiar with using something like the lasso, selecting a model. Of course, you would never use the estimates from the lasso, but you usually have to do some post-selection inference, which is quite cumbersome. And so the question is going to be, how do we evaluate these procedures when we think of model selection and estimation really as a joint problem? It's really the same problem, and separating them in two separate intellectual endeavors is perhaps not fully wise. So I'll try and skip over the details. The most important part is that even though this work is semi-theoretical in nature, there is an R package that implements a whole bunch of things. So there's a whole lot of very efficient routines for model selection and model averaging, especially for linear regression, but not limited to that. In particular, there are some implementations for GLMs, meaning if you are running high-dimensional logistic or probit regression, you can use the package. There's a whole lot of documentation out there. So this is just a plug for use the MOMBF package. The acronym for the package is a priori potentially incriminating, but it will become clear what we mean by MOMBF. So the idea is that we are considering non-local priors, which are usually specified in terms of moments, and BF stands for Bayes factor. So just a little review. This is mostly for myself. Yeah, I'm sure you guys are fully familiar with the paradigm. I have to remind myself what it is that we're doing. Yeah. So forget about the details. No need to get into what those integrals are. But I'm going to think mostly about Bayesian model selection. I will do some comparisons with alternatives. Some deeply rooted philosophers would say, oh, it's completely different from anything else, like penalized estimation or machine learning. I think it's kind of the same. And so we'll just talk about how these similarities can perhaps help us in establishing the sort of a large sample evaluation of Bayesian procedures. But if you think about the ingredients that go into a model selection setting from a Bayesian perspective, well, you do need a whole bunch of ingredients. You do need, of course, data. So this is, if you have data, you can carry out this endeavor. You do need a collection of models. What that means is quite general, right? So you may consider a logistic regression or a classification model with a bunch of potential predictors. You do need a sampling distribution in the Bayesian setting. So you are operating under a fully probabilistic scenario. This may be a weakness or strength depending on the problem. And you do need priors. And priors, of course, you can think of them as the usual story goes, prior beliefs on the possible values of these parameters and prior beliefs about the possible likelihood of these models. In reality, when you engage into a high-dimensional estimation problem, you probably have not much available to you at that stage. But the idea is that if you can specify these 4 ingredients, so it's a very simple recipe, then your inference and your selection strategy is intuitively trivial. Yeah? The idea is you basically evaluate the probability of how likely is a model given that I observed a certain amount of data. Of course, that probability depends on the prior, right? Because the prior kind of will determine the possible range of data sets you could possibly see, given your the weight you give to those realizations of theta parameters. And so that's for selection of models. And then inference is also trivial, right? So I don't need to read 2 books by Efren and Tibshirani to figure out how to do post-selection inference. I just look at the posterior expectation of data given y, averaging over models, right? So Bayesian model averaging is just so trivial, even I can understand it, right? So of course, these are 2 objects of interest. And what's useful to think about is perhaps what's going to happen when information grows. Are these objects going to behave nicely, or are they going to cause me trouble? And you probably know the answer. Yeah, the answer is, short answer is yes, they will behave nicely. Long answer is no. Yeah, depends on how you go. so the simplest possible example is the case of linear regression. So in linear regression, you have to decide how many predictors you plug in. So if you want to predict some continuous outcome y, and a common strategy which aims to, in a way, regularized, or if you like, reoriented ridge regression, is to use Zellner priors. Basically, what you do there is for every model combination, you use the information in the predictors to define the orientation of where the shrinkage should apply. And of course, the key element here is that you decide what kind of shrinkage to apply a priori. So the G prior, of course, makes your life a little easier because now, in order for you to decide what possible values of theta I need to come up with, I only have to really specify one parameter, right? That kind of defines shrinkage around those possible values. And so you would hope that this little cheat would help you in model selection settings, and it kind of doesn't, because what happens is that in finite sampling scenarios, once you're dealing with the data you're dealt with, you're basically thinking of this G as a tuning parameter, and so you have to think seriously about ways to decide how much shrinkage I want to apply to this parameter. And so this is kind of the point of this story. If you just operate non-informatively, you end up with paradoxes, and you end up with the selection of models which are overly conservative. Yeah, so you discover nothing, you publish nothing, and you're not happy. So, but from a general perspective, the way this works is very similar to other penalty strategies, right? So if you think about lasso or ridge, you have all sorts of alternative configurations of the shrinkage scenarios. In one dimension, that's the only degree of complexity I can think of. This is what happens. You have some sort of prior over the range of theta, and of course, depending on how precise you are around that shrinkage, you may select theta to be 0 or different from 0. And so the selection of that shrinkage parameter sometimes goes completely mindless. Yeah. So you say, well, just a sample size, or maybe a sample size, a function of the sample size and the number of parameters. Or you can go a bit more empirical, yeah. So if you follow Efren's recommendations, for example, you can estimate that shrinkage using the data twice, and then you pretend you haven't. But usually you have some sort of good operative characteristics of these scenarios. And so what am I doing here? Why am I worrying about this problem altogether? Well, it so happens that this sort of nice scenario, at least in a theoretical situation, defines a bit of an imbalance in terms of how efficiently you screen out garbage, how efficiently you screen out parameters that really should not be there, how efficiently you screen out, markers that really you shouldn't worry about. And so this is enclosed in these two statements. So when I think about the true model not being nested within any model I consider, say MK, and I look at the probability of that model given the data, well, so this is basically the probability of discovering new things, if you pardon my imprecise characterization of what I'm considering. This probability goes to zero exponentially fast in the sample size. However, if the true model is nested within the model you're considering, so what that means is that if you're looking into a scenario where really you could save yourself some spurious markers, well, then of course things are going to work out correctly, yeah? So the probability goes to zero, but the rate at which you screen out markers is pretty slow. It's only polynomial, right? So it's going to be n to the minus some number. And so this imbalance, what happens is that, especially in cases where you worry about high dimensions and removing a lot of spurious elements from your analysis, will define basically inconsistent results, at least as information grows. And so the idea is that perhaps we can reconsider the way we do shrinkage. And because in the Bayesian setting, you're really operating in a L0 setting, right? So you're really saying it's either zero or something completely different. Usually we're worried about how big are these tails or how much shrinkage I apply to these priors. But we've never really worried too much about behavior of this shrinkage around zero. So the behavior of this shrinkage around zero is kind of funny because in principle, the arrow defines, oh, this marker is absolutely zero important for my problem. Whereas the density around that arrow tells you the alternative version of the world, right? So it says, well, this marker is likely to have this kind of effect. And so it's a bit funny that in your alternative view of the world, the most likely value is actually zero, right? So intuitively, what we would like to have is an alternative view of the world that assigns zero probability to the marker when the effect of the marker is indeed zero. And so you get these funny-looking priors. I think that would have been a better name for non-local prior. Funny-looking priors would have been more interesting. That kind of give you a plausible value, then plummet to zero under the alternative hypothesis, and of course you have maybe a double-sided idea. So what happens if we consider these kind of priors? So these kind of priors actually came up in design settings where, if you're assigning patient to trials and you consider sort of a simulation scenario where under the alternative zero is the most likely value, you lose a lot of power. So the extension from that to model selection became pretty easy maybe around 10 years ago. So the idea is that you can operate with some standard densities. You just have to sort of, or if you like some standard shrinkage, you just have to modify them slightly so that they will kind of screen out things when they become non-important. So considering that the actual formulas doesn't matter, but the point of those formulations is that it's really not going to be analytically too different from ridge or normal shrinkage or something like exponential shrinkage or something of that kind. But the idea of the definition is that I would like a prior that for theta going to theta zero, what that means is that for the effect of this marker really approaching a null, I would like that prior to just push the probability of the model that I'm considering to zero. So it's quite quite stark in terms of shrinkage. And so, especially we are considering this case, so the case of the number, or if you like, the complexity of the models you're considering that depends on the sample size. Now, that's actually, as I was saying, that's perhaps semi-irrelevant if you think about linear regression or logistic regression or things of that kind. But as you reach for non-parametric or semi-parametric settings, by definition, your model complexity increases with sample size. And so maybe these theoretical considerations, even though they've been developed so far within simplified settings, may have something to say for more complicated settings. So what happens when this is the case? What happens when my model complexity goes up with sample size? Well, funny things happen, yeah? So if you are happy with your local shrinkage, the posterior probability of the true model goes to 0. Now, this is not as problematic as you can imagine. The idea is that you still get the mode of the model space, but your uncertainty around the possible models, it's so high that whatever inference you plan to do on model selection or post-model selection inference becomes questionable. And so the only way to actually do it, I should qualify that statement, yeah, but one way to do this is to use non-local priors, which guarantee that if you gain more information, you're going to get to the right model with probability 1. So of course, these are asymptotic considerations, yeah, so from a practical perspective, it's seemingly irrelevant. I'm like, I don't care about consistency. At the end of the day, I just want to assess what happens in finite samples. But for now, let amuse my my asymptotic tendencies and pretend that this is actually important. So of course, there's other ways to recover this fact, yeah? So, and of course, the easiest way to do it is to just make sure that you have a whole lot of shrinkage on the models you consider. Now, that's tricky to do because in principle, what you need to know is a good idea of the number of markers that will be meaningful in a problem, right? So if you can do that, then you can apply appropriate shrinkage and still recover a good behavior of the posterior probability. But so this is the main problem, and you can fix it if you use non-local priors. Now, without, once again, I apologize for the level of detail, but without thinking too deeply about what happens, the idea is that, if you remember, when I look into a non-local prior, I can rewrite it basically as a modified standard shrinkage procedure, right? So I basically add in some distance function, and then this pi L is going to be whatever shrinkage you love, yeah? So double exponential, Gaussian, ridge, doesn't matter. So any non-local prior you can rewrite that way. And the properties of this distance function is that as soon as you would like a distance function to be defined in a way that as soon as theta becomes consistent with the null effect, that prior will push, or the distance will push the prior to 0 as fast as possible. And so the implications in terms of, so this is what you care about when you do model selection. You care about how likely is it that you observe this data within the models you considered, in particular in this case within, say, a specific model K. Well, that's going to be exactly the same probability as you would see under a regular prior times something else which depends on that particular distance function you have defined. Now, the good thing about that is that that distance function will go to 0 if you include spurious parameters into your model. And so in a way, you have defined a data adaptive shrinkage method that doesn't need to worry too much about model size. Once again, in finite sampling scenarios, defining appropriate levels of shrinkage in terms of what's the likelihood of seeing, say, 10 versus 100 parameters is still important, but at least now you have a way to get out of the embarrassing situation of having to consider, well, how many parameters really would I like to see in my models? So remember, this guy here does all the work, or most of the work, and it only depends on It only depends on the data, right? So it doesn't depend on the prior on the model space. All right. So for linear models, what happens is that if the model complexity goes up, then exactly what you want happens. Yeah. So this particular distance function will go to 0 if you include spurious parameters, and that's all that slide says. Yeah. So forget the details; doesn't really matter. I want to get to some of the applications. Yeah. So now up to this slide, if you forget the details and just realize that this is what's happening, well, now I'm kind of happy about model selection in a situation of increasing complexity, in the sense that I know that at least if I gain more and more information, that kind of shrinkage scenario is going to allow me to screen out spurious parameters quite efficiently. Now, if I take a look at what these priors imply in terms of sort of possible realizations of your effects of interest, right? So these are, once again, so these are priors defined in a setting where you think the effect is not 0, right? So in principle, if I included also the other component, you would have a big mass at 0, and then alternative possibilities over 2 dimensions, yeah? So this is the highest number of dimensions I can imagine. And so if you think about what the posterior should be, as you include the likelihood, so imagine that the likelihood defines sort of a mode here, and then the posterior is going to average over that shrinkage. What is your posterior going to look like? Now that I go into estimation, I know that my posterior is likely to have up to 2 to the k modes, right? How do I make sense of that, right? So in principle, what I would like to see is a situation where this likelihood at the end is going to swamp out the spurious modes and make sure that I do have sort of a reasonable assessment of these parameters. And so this is what the next slide says. So unfortunately, I went a bit copy and paste on this. But the idea is that we want to look at modes and means of the posterior distribution. And so that slide just tells you exactly that. Yeah. So that slide tells you that when I look at the posterior mode, I'm going to have analytically modes in all the quadrants that I'm considering, but those modes are going to go down to 0 pretty quickly. Similarly for posterior means. And so these results do remain valid under complexity increasing with sample size. And this is actually what I really care about, because I do care about post-selection inference, so I do care about the Bayesian model averaging estimate. And so what happens there is that imagine that I do have a parameter that is not 0, then the posterior expectation, averaging over models, it's going to behave basically pretty much like the MLE at the true model, okay? So what that means is that, and everything else is going to go to 0 at a rate of 1 over n. And so this is something we like, right? So what that means is that if I have a true effect, my estimate is going to behave like the oracle, right, for increasing information, so asymptotically. If I do have a spurious effect, so if theta I is 0, meaning it's something I really shouldn't put in there, well, then that goes to 0 at a rate that is now double the rate of local priors in the case of moment priors, product moment priors, so n to the minus 2, or exponential in the case of inverse moment priors. So now that you're starting to think about convergence rates rather than just sort of asymptotic consistency, you are now starting to smell a possible benefit in finite samples. So I think I'm running out of time, so what I'm going to do, just give you a quick idea of a simulation study, and then think about maybe how this is relevant for more complicated model settings. Yeah. So the idea here is that we're comparing a whole bunch of things: non-local priors, SCAD, lasso, and of course there's a countable number of methods. But I would sort of say that SCAD tends to compare favorably to a lot of methods usually. And from the Bayesian perspective, we're considering sort of the gold standard, I think, for local priors would probably be having sort of a prior over the shrinkage as well. So we're considering a simple scenario, but we are looking at fixing the sample size to say 100 subjects and then increasing the number of markers or the number of predictors to from 100 to say 1,000, right? And so I think this scenario is usually the most realistic, and you can go all the way up. The package is actually quite efficient to deal with very high dimensions. So this is what happens if I look at prediction error. Also, we define this in a simulation setting. So as usual, as you can imagine, the simplicity of the lasso and the cheap computation comes at a cost in terms of performance usually. SCAD tends to work very competitively under in low dimensional settings, but as you start increasing, there seems to be something funny happening. We'll see why. So we'll open up these results. Yeah, Hyper-G and benchmark price actually surprisingly do work pretty well compared to other procedures. And of course, as you include moment and inverse moment price, you do much better. Of course, the idea here is that I'm really considering a situation where most of the parameters are really 0, which you hope that will be the case in many applications. So it's useful to open up these results in terms of what things are 0 and what things are not 0. And so when I look into parameters that should be there in terms of predictive accuracy, well, most methods are somewhat comparable in scale. And so this is what I was telling you, is that the action really happens for spurious parameters, because for theta 0, meaning if the marker really shouldn't be included into your predictive model or overall regression analysis, well, then this is where these priors really make a difference compared to other strategies. So there's some classical formulations of these priors where you can think of estimating, for example, a maximum a posteriori rather than doing a full Markov chain Monte Carlo inference. But computation is actually not too different, especially if you want to do full inference over these parameters. I think I'm getting close to the end. So I'll just conclude quickly. I wanted to show a case study, but I'll conclude quickly in terms of these considerations, right? So it seems silly to still worry about linear models and what happens when complexity increases with sample size. From applied perspectives, it's quite rare to really think about that's reasonable unless you're considering things like Facebook data. Or, from a biological perspective, in biological applications, it's rare to say that the number of parameters you're willing to plug in depends on the sample size in such a stark scenario, right? However, what does happen is that as soon as you reach for something like non-parametric or semi-parametric models, then by definition, so for example, if you reach for something like random forests or tree-based methods or kernel regression, well, then by definition, the complexity depends on sample size. And so in that sense, I think that the revising the way we apply shrinkage regularization in terms of this formal hypothesis testing setting could be potentially useful. So next project is going to be to start looking into trees. And I'm just going to show you something quick in one dimension. So this is the idea, right? So in one dimension, you don't expect different shrinkage properties to operate very differently. So here I just have a tree that would split the data into one component. And so what I can do is evaluate the likelihood of the split with respect to different prior settings. So if you like, you can think of that as a complexity penalty if you operate with a CART algorithm of something of that kind. What you see is that even in one dimension, a non-local prior is data adaptive and defines sharp precision of the selection of the split point. So that's actually augmented as you increase the number of dimensions. So there's big potential for some of these topics to be expanded into non-parametrics. So I'll just give you a quick idea of a study, because of course the next question is, well, when you do Bayesian inference, the usual complaint is that, well, I can't really do it for very large dimensions. So the reality is that you can, and as long as you are willing to remove all the garbage so that you don't have to carry out very heavy computation. And so especially for some of the simplest and actually well-performing non-local priors, your computation time to do an exploration of, say, 10 to the 7 updates for 10,000 predictors and about 200 subjects, it's about 4 minutes, which is something you can definitely do, yeah? So you can wait 5 minutes, get a cup of coffee, and then look at your results. So the idea is that you can do it. You don't need to be shy about using Bayesian methods to carry out some of these computations. So I'm done, sorry. I think the most important thing is to actually acknowledge the people that did most of the work. Definitely David, that used to be at Warwick, now it's in Pompeu Fabra, Barcelona. Val Johnson, that developed a lot of the theory for some of this stuff. Mark, that gave a lot of good ideas. And of course, your tax money that paid for it. But the idea is that the really key element is that we really want to make sure that even the mildest of these shrinkage scenarios will remove garbage at a rate that doubles what you would achieve under regular shrinkage.